Continuing our lecture on central force motion. So we saw that when you fed the data of the energy and the angular momentum inside the angular momentum responsible for central force motion, then we found r in terms of theta, and this r in terms of theta was directly calculated from the energy and angular momentum, and the final equation where r in terms of theta is this. This equation is very important, and this equation will tell us what are the possible orbits that can happen when there is a central force motion. See, logically, whenever you think of a central force, you will always think that only circular motion can happen or elliptical can happen. No, there are parabolic and even hyperbolas that can happen because of central force motion. So that's why mathematics is more important than your intuition. Okay, because intuitively you can think of central force motion is either causing a elliptical or a circular orbit, but mathematics is beyond intuition. It tells the entire story. So let us see step by step. Point number 1, E, the eccentricity, decides everything here. Remember, E, the eccentricity, decides everything. So if epsilon is 0, then remember that we are going to have a circular orbit. Okay, now question is how to know that if epsilon is 0 we are going to have a circular orbit. Okay, so look at the equation. Let's solve the equation. What happens to this equation when epsilon is 0? When epsilon is 0, we have only 1 by r equals to m alpha by L square. So r has only one value, and that value is unique. The value of r is unique, and this indicates that this has to be a circle, because only in a circular path the r does not change. The r is a unique value. Agreed? Second, what happens to the total energy if an object moves in a circular path? Let us see. So what was the total energy for a central force motion? So let me write it down. It consisted of the radial kinetic energy, which is half m r dot square. Then it consisted of the angular momentum, I mean the kinetic energy related to the linear velocity, which can be written in terms of angular momentum, which is 2, so L square by 2 m r square. And third, you had the potential, which is alpha by r. You added the potential, but potential was negative, that's why there is a minus sign in the end. Now what you do, now you put value of r equals to, what did you get? R, you got r as L square divided by m alpha. So when you put the information of the circular orbit radius inside the energy, what do you get? You find that your energy is amazingly negative. So that is m alpha, so minus of m alpha square divided by 2L square. Agreed? So what does a negative energy signify? A negative energy means that the object is bounded. And when the object is bounded, it means it is tracing a complete circular curve around the sun. So consider this is the sun, and if I have any other planet, and if I say that total energy of this planet is completely negative, so it is less than 0, it means that this planet is bounded, and somehow this planet will either trace a elliptical orbit or the planet will trace a circular orbit. So it can have out of two, any one can happen. So the very fact that energy is negative directly states that if the energy is negative, then we are going to have a bound state. By bound state, I mean the planet will have either a elliptical or circular orbit, and it will be bound to the sun forever and ever and ever, like our solar system. All the planets are bound to the sun because their energy is negative. They oscillate, they rotate in a particular orbit forever, ever and ever. Agreed? Next step is what happens. So consider second bit. What happens when your epsilon is between 0 and 1? So in the first case we considered epsilon as 0. Now we increase the epsilon little bit, but not so much. Then what happens to the value of energy? Then the value of energy will lie from negative value, that is m alpha square divided by 2L square. So the value of energy will oscillate between these two values. So total energy will be either negative, so it will be negative and less than 0, and total energy cannot be less than this. It has to be always more than this is the minimum value. In this case, there will be two values of R. Amazing, right? There will be two values of R. One will be R minimum and another will be R maximum. The moment you have two values of R, it is quite clear that there is going to be an ellipse, because only in ellipse there is a small r and there is a big R, only in case of ellipse. So here, if the planet is here, then this is the R minimum, okay, and if the planet is somewhere around here, then this is the R maximum. So whenever you have two values of R, one thing is sure, that the bound state is going to be a ellipse, because there are two values of R. What happens when epsilon is 1? So consider another case when the value of, so consider third case. In the third case, consider that the value of epsilon is 1. Okay. So when the value of epsilon is 1, then there are two cases. So so can you tell me when the value of epsilon will be 1? When the total energy will be 0. Now question is, how do I know? Remember the expression for epsilon? The expression for epsilon was root over of 1 plus 2m e divided by m alpha square. So this was the expression for epsilon. So if you only epsilon is 1 when the total energy is 0. In this case, there is a R minimum, and this R minimum is L square divided by 2m alpha, and R maximum is infinity. R maximum is where? Is infinity. It means this signifies that here we have a parabolic path. The trajectory is a parabola. Okay. So various values of epsilon will tell you the various possible orbits. Only when the energy, see, this is not a bound state. So when the energy is 0, do you think that the planet is going to trace out some particular orbit around the sun? No, this is not a bound state. Somehow the planet came near to the sun and then the planet got away. What do you mean by R maximum equals to infinity? It means the planet got away. So this is not a bound state. So third part is not a bound state. Agreed? So remember, bound state means there will be a stable orbit, and unbound state means there won't be any orbit. Agreed? So I hope things are clear about the circular motion. I mean about the central force motion. And epsilon greater than 1 will trace a hyperbola. Agreed? Now in the next and the last lecture of this of the central force motion, we'll find a differential equation that can tell us that can relate the force law of a central force motion with its orbit. Quite interesting, right? What I want to say here is that, see, up to the discussion we had till now, assume that the force is minus alpha by r square. We assume that this is the force because our potential was what? Our potential was minus alpha by r. And we solved all the equation related to this force. This force is a particular force that is a gravitational force. However, there can be many weird types of forces which have a weird dependence on r, and they are all some kind of circular, some kind of central force. There can be weird dependence of forces on r. So for example, if I give you an example that, hey, there is one more force and this force is also central because the force depends on r, and this is how the force depends on r, is some value of L cube divided by m r cube and a square plus 1. Don't you think this force is quite weird? The force is weird because, see, gravity had a r square dependence, but this force is having a r cube dependence. Is this a central force? Yes, it has to be a central force because we said all the central force has force which is a function of r, whether it be cube, whether it be square, or whatever. So now the problem is, if you are given the force, how can you find the r of theta? Because last example, because in our last lectures what we did, we used the energy approach. Remember, we used what approach? We used the energy approach. By using the energy approach, we solved everything. But now I tell you, if you are given a particular force and if you are asked a particular orbit, so what will be the orbit with respect to this force? Or the vice versa, if you are given an orbit, then what will be the force? In such cases, in such circumstances, how will you answer the questions of the central force motion? That we'll do in our next lecture.